Today we will start section 5.1, which is probability. And our first class for probability is going to be basic definitions, characterization, sample space, and etc. So by the end of this first section, we will be able to understand the meaning of an experiment, an outcome, an event, and a sample space. Describe the classical method of assigning probability, explain the law of large numbers, and relative frequency method of assigning probability. The probability of an outcome is defined as a long-term proportion of the number of times the outcome occurs. In probability, an experiment is any activity for which the result is uncertain. Each of the possible results of the experiment is called an outcome. The collection of all possible outcomes is called the sample space. An event is a collection of outcomes from the sample space. So let's do a simple exercise in order to better explain these concepts. What is an experiment? An experiment is a process. If there is a process with results, with a preset result, then so that means you know what are the possible results that are going to get out of this experiment or this process. Then the process will be called experiment. So what I will do now, I will give you a simple example. So for example, think about tossing the coin. And this is our starting point. So if you toss a coin, there are two possible results. Either you will see heads or you will see tails. So it is an experiment. So tossing the coin is the experiment. As soon as you have done the experiment, the next thing is sample space. So what is a sample space? A sample space is the collection of all possible results. So what are the possible results? So first I'm going to say this is the collection of all possible results. And then my question is, what are those for our experiment? So for us, this collection is going to be either seeing head or tail. And I'm going to stop there and I will write these two possible results, H and T, head and tail, in curly braces. And that's the way you will write a sample space. Generally, we will use the letter S to mean the sample space. Each individual result is called outcome. So each individual result is an outcome. So in this situation, there are two outcomes, and those are H and T. Event. An event for an experiment is a subset of the sample space. So subset means it is a sub-collection of the entire collection of the sample space. So what are possible events for this experiment? Well, think about nothing. That's an event space. So if we write curly braces with nothing inside, it is called null event, but it is an event. Or you can think about only H, that is a sub-collection, so that's an event. You can think about only T, that is a sub-collection, so that's an event. Or you can think about the sample space itself. These are all possible events for your sample space. So those are the different events for this experiment. Events are generally denoted by writing the letter E. So let's go back to our lecture now. The rules for probability is twofold. First and foremost, the probability of an event E will be denoted by writing P, and then inside parenthesis we'll write E. So P of E, or probability of E, for any event E is always between 0 and 1. Probability cannot exceed 1 precedes 0. So writing percentages for probability, even though it's a very common tactic, is wrong. Never write percentages for probability. Probability has to be a number between 0 and 1. When we write percentages, that is called proportionality. Then the next concept is the law of total probability. In an experiment, the sum of the probabilities of all the outcomes must be equal to 1. For example, in our tossing the coin, we have two outcomes, H and T. So if I find probability of H and I find probability of T, the sum has to be equal to 1. If you have these two rules followed, then we call the system a realistic probability model. And if at least one of these two is failing for a model, then that model cannot realistically describe a probabilistic model. Classical method of assigning probabilities. N of E is the number of elements in the event space E. N of S is the number of elements in the sample space S. The number of elements in the event space over the number of elements in the sample space is called probability of the event E. So it's how many elements are there in the event space over how many elements are there in totality in the sample space is going to describe the probability of an event, and this way of assigning probability is called assigning probability by the classical method. Law of large numbers. As the number of times that an experiment is repeated increases, the relative frequency or the proportion or the probability of a particular outcome tends to approach the probability of the outcome assigned by the classical method. For quantitative data, as the number of times that an experiment is repeated increases, the mean of the outcomes tends to approach the population mean. For categorical or qualitative data, as the number of times the experiment is repeated increases, the proportion of times a particular outcome occurs tends to approach the population proportion as well. That brings us to the concept of relative frequency method of assigning probabilities. The probability of event E is approximately equal to the relative frequency of the event E. That is, probability of E is frequency of E over the number of trials of the experiment. Now, there are two primary ways and reasons why we will assign the probabilities in different ways. If you are thinking of an experiment where the outcomes are equally likely, or so to say, in depiction of the outcomes of the experiment, no human factor is involved. For example, if you are tossing a fair coin, there is no way someone can control whether the face head or tail can come. That is called equally likely outcomes. Both heads and tails are equally likely. And in that situation, we will assign probability using the classical method. But if your experiment has human factors involved when it comes to outcomes, for example, you are trying to understand number of illegal parkings in a parking lot. Now think about two different situations. You went to Walmart and you were trying to find out how many cars are illegally parked. And you went to the local courthouse and you were trying to understand how many cars are illegally parked. Clearly, people are more scared of doing illegal activities when law and order are in the vicinity. So in front of the courthouse, you will find less number of cars parked illegally. So if I'm assigning a probability to an experiment of what is the probability that a randomly selected car will park illegally, the process involves human conditions. The outcomes are not equally likely. They depend on other external conditions. So the better way of assigning probability is going to be assigning using the relative frequency method. We'll talk about both methods. We will solve examples. So we're going to solve a long example to start this process. So we will remember certain things for this example. This example is, consider the experiment where a fair die is rolled twice. The following events are counted for each roll. So what are the things? You have two fair dice. Each of them have 6 sides, numbered 1 through 6. Now, we're going to call a roll a low roll if your outcomes are either 1 or 2. We will call it a medium roll if your outcomes are 3 or 4. We will call it a high roll if your outcomes are 5 or 6. We will call it an odd roll if your outcomes are 1, 3, 5. And an even roll if your outcomes are 2, 4, and 6. The first question that we have for this experiment is construct a tree diagram for the experiment. Make sure you use the outcomes and not the events. So what we're going to do, we're going to first say first row. That's where we're going to start our problem. In the first roll, I have 6 different outcomes. And these are 1, 2, 3, 4, 5, and 6. Now, if I consider the second roll, then remember each of these 6 outcomes are going to give you 6 more outcomes. For example, the first roll you had 1, but now you have 1, 2, 3, 4, 5, and 6. As different outcomes. So the tree diagram is as follows. You have one root giving you 6 different branches, as I'm depicting this way. And then each of these branches are giving you 6 different new branches. This process is going to help us write down the sample space faster. So similarly, you can get 1, 2, or 3, or 4, or 5, or 6. So that's what it is going to look like. For 3, the same thing. You can get 1, 2, 3, 4, 5, or 6. For 4, I can get 1, 2, 3, 4, 5, or 6. 5, 1, 2, 3, 4, 5, 6, and for 6 you get 1, 2, 3, 4, 5, 6. And that diagram is called a tree diagram. Use the tree diagram to construct the sample space. How do I do it? Remember, your sample space is a set, so you're going to write it inside curly braces. And how we're going to write down the elements? Because we are talking about first and second, we're talking about ordered pairs. So the way we're going to write it, I get 1 in the first roll, 1 in the second roll. So 1, 1, 1, 2. So these are all 1s in the first roll. 1, 3, 1, 4, 1, 5, and 1, 6. These are my 6 different outcomes. Similarly for 2, I get 2, 1, 2, 2, 2, 3, 2, 4, 2, 5, and 2, 6. And we will keep doing it for 3 and 4. So the next one is 3, 1, 3, 2, 3, 3, 3, 4, 3, 5, 3, 6, 4, 1, 4, 2, 4, 3, 4, 4, 4, 5, and 4, 6. I have 12 more to go. I will start with 5 now. 5, 1, 5, 2, 5, 3, 5, 4, 5, 5, 5, 6, 6, 1, 6, 2, 6, 3, 6, 4, 6, 5, and 6, 6. And that's the total sample space. So if someone asks you how many elements you have in there, remember the first roll gave you 6, Each of these 6 give you 6 more, so it's 6 times 6, 36. So number of elements in the sample space, and this is how we are going to write it, is 36. Very important in computation of the probability. Because as you can possibly imagine, rolling a dice is also an experiment where you have equally likely outcomes. Whether the face up is 1, 2, 3, or 4, or 5, or 6 doesn't depend on the person who is playing. So they are equally likely outcomes. So assigning the probability will be done using the classical method. And we will answer that question very soon. The sample space is the collection of possible outcomes of an experiment. Explain why the sample space is not defined as the collection of all possible events. And that is a kind of an open-ended question. So what I want you to understand, just think about the analogy of building a house. When you're building the house, you start building with a little piece of a brick, a piece of a wood. You don't bring an entire wall and attach one other wall to bring to build the house. You start with the smallest building blocks. So what I say to answer this question, I say that since each outcome is an event, but not all events are outcomes. So it's like saying each brick is a building block, which is a part of the wall, but each wall, even though it is a building block, might not be a brick. So the smallest building blocks are the bricks. So each outcome is an event, but not all outcomes are, not events are outcomes. Hence, the smallest building block are the outcomes. So in the sample space, we use outcomes, not events. Find the probability of observing a 1 followed by another 1. What method of assigning probability are you using and why? So remember, we are talking about the event which is described by first roll 1, second roll 1, and there is exactly one of those events. So number of elements in E is 1, whereas number of elements in S is 36. And if you remember the classical definition of probability, it is number of elements in the event space over number of elements in the sample space. So you get 1 over 36. And I already used the classical definition. Why did I do it? So to answer the second two questions, we'll say we are using the classical definition as there is no human condition involved. A person doesn't determine whether the roll is going to end up in 1, as the outcomes are equally likely. And that would answer this part of the question. So we'll go ahead and answer the next one. Find the probability of observing 2 high die rolls. So now I want both of the rolls to be high die rolls. What method of assigning probability you are using and why? So this portion of the question we have answered. So I'm just going to go ahead and say that same as part D. But we want the event where both rolls are high, and remember high rolls are 5 and 6. So how many ways it can happen? Well, you can get 5 and 5. It can get 5 and 6. You can get 6 and 5, or you can get 6 and 6. These are the 4 possibilities. So probability of this event is number of elements in the event space over number of elements in the sample space. So it's 4 over 36. We can go ahead and write it as 1 over 9, or if you're writing in the decimal form, round to 4 decimal places. So if I do 1 over 9, I'm going to get 0.0 believe that's going to be 1, 1, 1, 1, rounded to 4 decimal places. What is the probability of observing an odd die roll followed by an even die roll? So write down the even space first. Odd followed by even. So I can do 1, 2. I can do 1, 4. I can do 1, 6. What else I can do? 3, 2. 3, 4. 3, 6. 5, 2. 5, 4, 5, 6. And that's it. That's the even space where an even die is following the odd die. And you see there are 9 of them. So I will say probability of this event is number of elements in the even space divided by number of elements in the sample space. And that is going to be 9 out of 36, which is 1/4. And that's 0.25. Next one. What is the probability of observing an odd die roll and an even die roll in no particular order? So now I do not want the odd to be the first one or the even to be the first one. So what I can have in this even space, everything that I have had previously. So I can have 1, 2. I can have 1, 4 because I just want one odd, one even. 1, 6, 3, 2, 3, 4, 3, 6. So just like the last one, you can actually copy and paste. And then 5, 2, 5, 4, 5, 6. On top of that, I might have 2, 1. First even, then on. Nothing wrong with that. I can have 2, 3. I can have 2, 5. Or I can have 4, 1, 4, 3. 4, 5, 6, 1, 6, 2, or 6, 5. So now I have 18 of them. So probability of this event is going to be number of element in the even space over number of element in the sample space, and that is 18/36, which is 1/2 or 0.5. The next question is asking you, why is this different from your answer in the previous exercise? Well, you will clearly say that the last exercise enforced ordering. Enforced odd followed by even. This one didn't. So I did not have to restrict myself. I had more outcomes in my even space. Find the following probabilities. 2 high die results. So I think we have done it once before. So let's do it one more time. 2 high dies mean you can get 5, 5 or 5, 6 or 6, 5 or 6, 6. Since there are only 4 of them, I will say probability is number of elements in the even space over number of elements in the sample space. So 4/36, which is 1/9, and I would say that's 0.1111 rounded to 4 decimal places. Exactly 1 medium die result. Medium is 3 or 4. So I can get 1, 3, 2, 3. Remember, I cannot have 3, 3 because then we will have 2 medium die. I can have 5, 3, not 4, 3 though. I can have 6, 3. And that's all we can have with 3 in the second place. But no one is saying that 3 has to be in the second place. So I can go ahead and say that 3, 1 can be an option. 3, 2 can be an option because I still have exactly 1 medium die. 3, 5, 3, 6. So these are all the results with 3. And I have to do it with 4. So 1, 4, 2, 4. Skip 3, 4 and 4, 4. So now you have 5, 4 and you have 6, 4. And then these are all the results with 4 in the second place. And now we will start putting 4 in the first place. So 4, 1, 4, 2, 4, 5, 4, 6. So how many of them I have now? Probability of this event is the number of elements in the event space over number of elements in the sample space. And I think I have 12 of them. So it's 12 over 36, which is 1/3, and that's 0.3333 rounded to 4 decimal places. Okay, carry on. No Lodi results. So this time you want no Lodi. So what you can do, write down the sample space and the event space for this one. No Lodi means you cannot have 1 or 2. So I will say what we can have, say we can have 3, 3, 3, 4, 3, 5, 3, 6, same thing with 4, 4, 3, 4, 4, 4, 5, 4, 6, 5, 3, 5, 4, 5, 5, 5, 6, 6, 3, 6, 4, 6, 5, and 6, 6 are all my outcomes. I don't have 1 and 2. And how many of them I have? Well, if you count, you will see that there are 16 of them. So probability of E is number of elements in the event space over number of elements in the sample space. So that's 16 over 36. If I simplify that, I will get 4 over 9, and that should be equal to 0.4444 rounded to 4 decimal places. At least one high die result. Now this is where we have to be a little careful. At least one high die means you can be one high die or both of them can be high die. So let's write down what we have. So I can have 1, 5 because I want at least one of them. I can have 1, 6. I can have 2, 5. I can have 2, 6. 3, 5. 3, 6. 4, 5. 4, 6. And as I said, no one told me at least one high die mean both of them cannot be high. So I can say 5, 5 is a good option. 5, 6 is a good option. 6, 5 is a good option. 6, 6 is a good option. But is that all? Well, no, because why we have to assume that only the second place or the first place is high. So now you're going to say 5, 1 is a good option. 6, 1, 5, 2, and see all I'm doing is flipping the order pairs. 6, 2. 5, 3, 6, 3, 5, 4, 6, 4, 5, 5, if I flip it I get the same thing, so I'm skipping it, 6, 5, but it is already there, and 6, 6 is already there too, so that's it. I'm going to stop there, and these are all my possible outcomes. So probability of this event is number of elements in the event space over number of elements in the sample space. I actually have to count. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So this is 20 over 36, which is 5 over 9. And if I want to write it in the decimal values, then this is 0.5556 rounded to 4 decimal places. At most one medium die result. So this is like the last one. You want at least one of 3 or 4. Both of them can be 3 or 4. So let's write down E. Oh no, this is said at most one medium. So cannot be both medium. So at least I can have a situation with no medium, no 3 or 4. If I had 3 or 4, then there should be exactly one of them. Cannot cross one. So the event space can be 1, 1. Nothing wrong with that. 1, 2. 1, 3, 1, 4, 1, 5, 1, 6, all of them are good. 2 is similarly, all of them are good. 2, 1, 2, 2, 2, 3, 2, 4, 2, 5, 2, 6. When I'm writing 3, I'm a little careful. 3, 1 already have given you one medium. 3, 2 has given you one medium. So you cannot have 3, 3 or 3, 4. But 3, 5 is good. So that's 3, 6. For 4, it's similar. 4, 1, 4, 2. 4, 3 cannot be there. 4, 4 cannot be there. 4, 5 is good. 4, 6 is good. 5, all of them are good. 5, 1, 5, 2, 5, 3, 5, 4, 5, 5, 5, 6, 6, 1, 6, 2, 6, 3, 6, 4, 6, 5, 6, 6, all of them are good. So what we have done so far, we have just written the sample sets. Let's count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32. So we'll say probability of this event is number of elements in the event space over number of elements in the sample space. And I say this is 32 over 36, which simplifies to 8 over 9. And I get to say that this is 0.8889 rounded to 4 decimal places. Answers my question.